All right, we want to talk about residuals, residual plots, and S, which is the standard deviation of the residuals. All right, and so we're going to talk about these three ideas together. First things first, a residual is the observed minus the predicted. Sometimes you'll see it says actual minus predicted, but I like ROP, R-O-P. Residuals is observed minus predicted, and it measures how far a data point is from the line, okay? An individual piece of data is an observation. So for me, my shoe size is an 11.5 shoe. My height is 74 inches tall. The least squares regression line can get, so that's my observed value, is 74 inches tall. It's my observed Y. My predicted Y is whatever plugging 11.5 in to my equation would get me, okay? So my observed value would be 74 inches. I would have to have an equation of a least squares regression line, and I would plug in 11.5, I'd use my X value to get a Y value and subtract it 2, and that's my residual. Pictorially, this is what your residual looks like. A positive residual is observed minus a smaller predicted would get you a positive number. Here, the observed is less than the predicted is getting me a negative number. And so a negative residual means you're below the line. A positive residual means you are above the line. A zero residual means you are on the line, okay? And small residuals are close to the line. Big residuals are farther from the line, okay? So let's try an example real quick. So heart rate before and after a brisk walk. All right, this is the least squares regression line equation that we're going to use. And we're told what my standing heart rate, this is my standing heart rate before a long walk when I just am normal. And we'll calculate it, what it ought to be after a long walk, okay? So not what it ought, what it's predicted to be. So I need to get a residual. We need observed minus predicted. I already know the observed value. The observed is 68. That is what was observed after the brisk walk. The predicted needs to be gotten by my prediction equation. So we'll do Y hat equals 1.58 times my X value, which is 60, minus 30.16, and I get 64.64. And so my residual is 3.36 beats per minute. And what does it mean? How do I interpret that? Well, my observed heart rate was 3.63 beats per minute above the predicted, greater than the predicted heartbeat rate after a brisk walk, okay? So next, we want to compare scatter plots and residual plots, okay? So this was a scatter plot, which has a line of best fit drawn through it, and you can see the residuals, right? This guy here is a negative residual. This guy here is a positive residual. And if I go over to this graph and I graph all of my positive residuals and all of my negative residuals on my X scale, so this X scale is just listing them all from left to right, okay? But usually what you do is you actually just keep them at the same X's, all right? But it's showing how far above you are. So this guy, see how this guy's really, really tall, okay? He's at about 35, but he's predicted to only be at about 22, okay? So he's about 12 or 13 above where he's predicted to be, maybe even 15. And you can see here, that's that dot right there, and he is 15 above the line, okay? This guy right here is like right on the line, okay? And he's probably this point right here, which is like right on the line, okay? So these residuals are showing how far you are above or below the line. So it's basically, if you just took this line and flattened it out to horizontal and kept these straight up perpendicular above and below the line, and you call that horizontal 0 because all the dots that are on the line have a residual of 0. Like these two dots both have a residual of 0. Okay, and they're probably both right there stacked on top of each other, or maybe it's there and there. Okay, so those residuals of 0 are the ones on the line. All the positive residuals are the ones above the line, and all the ones below the residuals are below the line, negative residuals. Okay, so a scatter plot, we want our points to line up and be relatively linear, right? And we have a correlation coefficient that measures that. The residual plot should be scattered after we've done it. And the reason why we call it a residual plot, so it's kind of funny. We want the scatter plots to be linear. We want the residual plots to be scattered. But we're checking is after we use the line to make predictions, is there a residual pattern left over that the line didn't account for? If there's a residual pattern left over, then it means that the line wasn't the best model that we should have used, but there's a different model that's maybe curved or something that we should have used because we don't want a residual pattern. And this one doesn't seem to have a residual pattern left over. Let's just look at a quick example of a few, okay? So this one, see how it's sort of getting wider as you go down the line, okay? And so the residual plot would look like this. See how it's getting wider as you go from left to right, okay? It's getting more and more scattered around the line, okay? But it's staying symmetric, above and below, above and below, above and below, but it's getting wider as you go from left to right. So this would be residual plot D, okay? This one, see how it's curved? So we're mostly below here. Oh, then we're mostly above here. Ah, my pen is not cooperating. Sorry. And then we're mostly below again. Okay. And you can see here, it's above, it's below, and below on the two sides. And so this would be scatter plot B. These two are relatively the same width above and below all the time. The same width above and below all the time. But this one's a lot more spread out. And so notice we're going up and down 15 below the line. This one, we're only going up and down like 5 or 10 above and below the line, right? You see that? Okay. So this one's a tighter band, goes with C. This one's more spread out, but it's scattered A. So both of these are good residual plots because there's no residual pattern. It is scattered. And if you do zoom 6 on a residual plot, I'll show you how to make a residual plot on your calculator. If you do a zoom 6 on your residual plot, it would spread out this scale so that these two would actually look almost exactly the same. But you want it to be completely scattered. You don't want to have a residual pattern left in your residual plot. All right, the last thing I want to talk about is S, the standard deviation of the residuals, which you can think about one of two ways: the average distance from the line, or what I like to call the typical prediction error. Okay, so my line is a prediction, right? So line, prediction. And a deviation or distance is how far away you are. And average and typical are sort of synonymous, okay? So these both say the same thing. Typical prediction error or average distance from the line. Okay, this sounds a lot more like average distance from the mean, but we're not measuring from the mean because the mean is changing for all of these. But if you imagine sort of like these 5 or 6 dots, the mean might be right there. And these few dots, the mean's right there. These few dots, the mean's right there. And these few dots, the mean's going to be maybe right here. But we're not measuring from the mean, we're measuring from the line, okay? And here, this is the same two graphs that we showed a second ago. This is a little bit more spread out than this one. So on average, this one would have an S that is, so the S from plot 2 would be greater than the S from plot 4, okay? Because on average, we're farther from the line. So it's more spread out around the line. Here it's more compact around the line. And that's what we're measuring when we talk about S. This is the formula for it. This measures the actual minus the predicted. Oh, that's called a residual. That's why it's the standard deviation of the residuals, because we're getting every single point's residual. We're squaring them. We're adding them up. We're dividing by n minus 2 and taking a square root. And this 2, you can think about it because we have two variables, x and y. right? We're using a y here, and then we use an x to predict a y here. There's two variables, is why we divide by n minus 2. But it looks just like your standard deviation formula. Instead of doing x minus x bar, we're doing y minus y hat, squaring them, adding them, n minus 2 instead of n minus 1, and then we take a square root. So that would be like the variance before you square root it, and then you square root it, and you get down to a standard deviation of the residuals, okay? And that's it. So good luck. See you soon.